The night sky on a clear, crisp evening seems a place of serene permanence. We see the familiar constellations, the steady glow of planets like Jupiter and Mars, and the comforting sweep of the Milky Way. It all appears so orderly, so predictable, but this magnificent celestial clockwork hides a profound and unsettling truth. Beyond the light of any star, adrift in the unimaginable emptiness of interstellar space, are wanderers. These are not comets or asteroids, but entire worlds, untethered from any sun, silently hurtling through the cosmic dark. They are rogue planets, the galaxy's hidden population, and they represent a silent, cosmic threat that challenges our perception of a safe and stable cosmic neighborhood. These dark worlds are the ultimate cosmic ghosts. They emit no light of their own, save for the faint residual heat left over from their violent formation billions of years ago. Imagine a world larger than Earth, maybe even the size of Jupiter, cloaked in perpetual darkness, its surface frozen to temperatures that make our coldest Antarctic nights seem balmy. It follows no set path, no predictable orbit. Instead, it drifts on a lonely, chaotic trajectory through the galaxy, a phantom object whose existence we can only infer. This is the nature of a rogue planet, a world without a star, a home without a sun, an orphan of a long-forgotten solar system, forever roaming the galactic wilderness. The sheer scale of this idea is, honestly, difficult to comprehend. Our galaxy, the Milky Way, is home to hundreds of billions of stars. For a long time, we assumed that most planets would be found orbiting these stars, just as Earth orbits our sun. However, recent scientific models and observations are painting a very different picture. It now seems that for every star you see twinkling in the night sky, there could be dozens, perhaps even 100, of these rogue worlds drifting unseen between them. The galaxy, it turns out, might be teeming with more planets in the dark than planets basking in the light of a parent star, a staggering realization. This hidden multitude transforms our understanding of the cosmos. It means that the space between stars is not as empty as we once believed. It is populated by a vast, invisible armada of cold, dark worlds. They are the silent majority of the planetary family. While we look up at the familiar lights, these cosmic wanderers continue their endless journey, their paths dictated by the complex gravitational dance of the galaxy. Most will never come close to another star system, but with so many of them out there, the laws of chance suggest that encounters, however rare, are not impossible. It is a sobering thought that the greatest threat might not come from a visible, predictable source, but from the darkness itself. So, where do these cosmic orphans come from? How does a world break free from the powerful gravitational embrace of its parent star to begin its lonely journey? The answer lies in the chaotic and often violent youth of planetary systems. When a star is born from a collapsing cloud of gas and dust, it is surrounded by a swirling protoplanetary disk. Within this disk, countless smaller bodies, planetesimals, collide and merge, gradually building up into full-size planets. This process is far from gentle. It is a cosmic game of dodgems on a colossal scale, a period of intense gravitational jostling and competition for space and material. Imagine a young solar system, not unlike our own in its early days. Several gas giants, similar to Jupiter and Saturn, are forming and migrating within the system. Their immense gravity acts like a powerful slingshot. As these giants move, their gravitational fields can intersect and interact in unpredictable ways. A smaller Earth-sized planet could find itself caught in a gravitational tug-of-war between two of these behemoths. If the timing and alignment are just right, the smaller planet can be accelerated to incredible speeds, far exceeding the star's escape velocity. It is then flung out of the system entirely, ejected into the cold, dark void of interstellar space. This process of planetary ejection is not a rare or unusual event. In fact, computer simulations of solar system formation suggest that it might be a standard feature of planetary development. For every stable, orderly system like our own that we see today, many more may have started with more planets than they ended up with. The survivors are the ones that settled into stable orbits, while the unlucky ones were cast out. It is a brutal form of cosmic natural selection. A rogue planet is, in essence, a refugee from a planetary system's turbulent past, a testament to the gravitational chaos that governs the birth of worlds. The path of such a planet is then rendered utterly unpredictable. Once free from its home star, its trajectory is governed only by the faint, collective gravitational pull of the galaxy itself, and any nearby stars it might pass. It doesn't orbit anything in a neat, elliptical path. Instead, it follows a long, sweeping arc through the galaxy, a journey that can last for billions of years. Over these immense timescales, its path can be subtly altered by distant massive objects, making its future position almost impossible to calculate unless we can spot it relatively close to us. It is a cosmic cannonball, fired from an unknown source billions of years ago, and its destination is a mystery. The prospect of a rogue planet entering our solar system is the stuff of science fiction, but the potential consequences are grounded in the very real laws of physics. The most obvious threat, of course, is a direct impact. A collision with a world even the size of our moon would be an extinction-level event far beyond anything we have ever experienced. An impact with an Earth-sized rogue would be utterly cataclysmic, resulting in the complete sterilization of our planet's surface, melting the crust, and boiling the oceans away. It would be a literal resetting of Earth's geological and biological clock, an event from which life might never recover. However, a rogue planet would not need to hit us directly to spell disaster. Its gravity alone would be a weapon of immense power. Imagine a Jupiter-sized rogue passing through the outer solar system, somewhere near the orbit of Neptune. Its immense gravitational pull would act like a wrecking ball, destabilizing the beautifully balanced orbits of our own planets. It could tug Neptune and Uranus into new elliptical paths. This disturbance would cascade inwards, disrupting the asteroid belt and the Kuiper belt, sending a deadly shower of comets and asteroids careening towards the inner solar system, including Earth. We would face a bombardment lasting for centuries. Furthermore, a close pass could have a direct and devastating effect on Earth itself. If a large rogue planet were to pass even millions of miles from us, its gravity could trigger catastrophic geological upheaval. The gravitational stress could stretch and deform our planet's crust, leading to planet-wide earthquakes of unprecedented magnitude and volcanic eruptions on a global scale. It could even affect our orbit around the sun, potentially tugging us into a path that is either too hot or too cold to sustain life as we know it. A rogue planet doesn't need to strike us to destroy us, it merely needs to pass by. There is also a more speculative, yet fascinating possibility. A rogue planet, though frozen on its surface, could potentially harbor life. A large rocky world with a thick atmosphere and residual heat from its core could maintain liquid water oceans beneath a thick crust of ice. It is conceivable that life could exist in such an environment, powered by geothermal vents rather than sunlight. If such a world were to enter our solar system and shed material, perhaps through tidal forces, it could seed our corner of the galaxy with extraterrestrial microbes. While a fascinating scientific prospect, it also carries an unknown biological risk, a potential panspermia event with consequences we cannot possibly foresee. How do you find an object that is nearly invisible, wandering unpredictably through the dark? Detecting rogue planets is, honestly, one of the greatest challenges in modern astronomy. Traditional methods of finding exoplanets, like watching for the dimming of a star as a planet passes in front of it, the transit method, simply do not work. These worlds have no star to transit. So, instead, astronomers have to rely on more subtle and, well, ingenious techniques, chief among them being gravitational microlensing. This method uses the principles of Einstein's theory of general relativity as a sort of cosmic magnifying glass. Gravitational microlensing happens when a massive object, like a rogue planet, passes almost directly in front of a distant background star from our point of view. The rogue planet's gravity is strong enough to bend the space-time around it. This warped space acts like a lens, focusing and momentarily brightening the light from the distant star. The duration and pattern of this brightening event can tell astronomers a great deal about the object that caused it, including its approximate mass. If the brightening event is not associated with any visible foreground star, it is a strong candidate for a rogue planet. It is a fleeting chance alignment, but honestly, it is our best tool for finding these ghosts. Another promising method involves searching for the faint heat these planets radiate. Although their surfaces are frozen, their cores may still retain some of the immense heat from their formation. This means they emit a tiny amount of energy in the infrared part of the spectrum. Highly sensitive infrared telescopes, operating in space to avoid the warmth of Earth's own atmosphere, can scan the skies for these faint, slow-moving heat signatures. It's kind of like searching for a faintly warm needle in a cosmic haystack that is at absolute zero. It is incredibly difficult, but not impossible with the next generation of observatories. New and upcoming observatories are set to revolutionize this search. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will be a master of this technique. It will survey a huge patch of the sky, observing hundreds of millions of stars, specifically looking for these telltale microlensing events. Scientists anticipate that Roman could discover hundreds, if not thousands, of rogue planets, giving us our first real census of this hidden population. By understanding how many there are, and what sizes they are, we can begin to build a much clearer picture of the potential risk they pose and their role in the galaxy's evolution. Let's imagine the unthinkable happens. Astronomers detect a rogue planet on a collision course with Earth. It is decades away, but its trajectory is certain. What could we, as a species, possibly do? The challenge is one of sheer scale. We are not talking about deflecting a small asteroid. We are talking about changing the path of an object with the mass of a planet. The energy required is almost beyond comprehension. Our current technology would be like trying to stop a charging bull with a feather. However, scientists have considered several theoretical strategies, all of which push the boundaries of our capabilities. The most discussed concepts involve some form of kinetic impactor or a gravity tractor. A kinetic impactor would involve sending one or more massive, high-speed spacecraft to collide with the rogue planet. The goal would not be to destroy it, but to impart just enough momentum to slightly alter its course. Over the vast distances of space, even a tiny nudge, applied decades in advance, could be enough to make the planet miss Earth entirely. A gravity tractor is a more subtle approach, involving parking a heavy spacecraft near the rogue planet and using its own tiny gravitational pull to slowly, gently tow the planet onto a new, safer course over many years. For a larger rogue, or one detected with less warning time, more drastic measures might be considered. The use of nuclear explosives is a recurring theme in planetary defense scenarios. A series of strategically placed nuclear detonations near the surface of the rogue planet could vaporize a portion of its crust. This vaporized material would be ejected into space, creating a powerful rocket-like thrust that would push the planet in the opposite direction. This is an incredibly high-risk strategy. A poorly calculated detonation could fracture the planet, creating multiple, equally dangerous fragments, or simply fail to provide enough of a push. The fundamental limitation of all these strategies is time. Early detection is everything. A threat detected centuries in advance is a manageable engineering problem. A threat detected only a few years away is an unavoidable catastrophe. This underscores the absolute necessity for continued investment in sky surveys and detection technologies. It also highlights the need for unprecedented international cooperation. Responding to such a threat would be a project for all humanity, requiring the combined resources, knowledge, and industrial capacity of the entire world. It is a challenge that would force us to work together as a single species with a common goal: survival. While rogue planets present a potential, albeit remote, existential threat, they also represent an incredible scientific opportunity. These wandering worlds are not just dangers, they are cosmic artifacts, time capsules from distant and unknown solar systems. If we could ever study one up close, perhaps with a robotic probe, the discoveries would be profound. We could analyze its composition to learn about the building blocks of another planetary system. We could study its frozen atmosphere and geology, gaining insights into planetary formation that are impossible to get from the stable, evolved worlds in our own solar system. They are a window into the diversity of planetary creation. The study of rogue planets also forces us to reconsider the conditions under which life might exist. For decades, our search for life has been focused on the habitable zone around stars, the narrow band where liquid water can exist on a planet's surface. Rogue planets challenge this paradigm. A large rocky world with a thick hydrogen atmosphere could trap its own geothermal heat, maintaining liquid water on its surface even in the freezing dark of interstellar space. The existence of such worlds would mean that the potential homes for life in the galaxy are far more varied and numerous than we ever imagined. Life might not need a sun after all. Ultimately, the existence of rogue planets teaches us a valuable lesson about our own place in the universe. It reminds us that our solar system, with its stable orbits and life-giving sun, is a precious and perhaps fortunate arrangement. We live in a calm harbor, but it is a harbor that sits on the shore of a vast and sometimes chaotic cosmic ocean. The universe is not a static diorama, it is a dynamic, evolving place, filled with both wondrous beauty and immense indifferent power. Acknowledging the existence of these dark wanderers fosters a sense of humility and perspective. The hunt for rogue planets is therefore more than just a matter of planetary defense. It is a quest for knowledge. It is about charting the unseen territories of our own galaxy, and understanding the full story of how planets are born, how they live, and how they die. Or in this case, how they are cast out to wander forever. By searching for these ghosts in the dark, we learn more about the fundamental processes that shaped our own world and our place within the grand cosmic narrative. The wanderers in the dark are a reminder that there is always more to discover, and that the universe is, and always will be, full of wonders.